Hey, let's go over the proof of work system and the 51% attack scenario. So, what is this proof of work system? Well, it's one that requires blockchain contributors to spend some time doing computational work in order to add blocks to the blockchain. Rather than allowing anyone to freely add a block of data, you have to spend computational power, including CPU time and electricity costs, in order to add a block. The immediate benefit is that this deters attackers from trying to rewrite the entire blockchain history with corrupt and invalid data. It's going to be financially expensive for them to try. So, one question you might be asking is, how can it be expensive for attackers to try and replace a blockchain, but still be reasonable for honest contributors to spend the time and money to add, well, a new and valid block? Well, consider that in a decentralized blockchain network, any peer has the capability of submitting a new chain to the system. Adding one block is not such an expensive task. As long as a block is valid and is based on the existing valid chain from the Genesis block onward, that chain will be accepted by all peers in the blockchain network. However, a malicious individual can't just pay the cost for adding one new block. They may try to just edit one block in the blockchain history, but by modifying one block, you change its hash, and this breaks a continual line of last hash references in the entire chain, starting from their modified block. Therefore, the hash of every block, including that block and the ones afterward, get corrupted. The only option is to pay the cost of rewriting all of those blocks over again. So this is going to be really expensive for the blockchain attacker, whereas it's relatively affordable to add a block when you're just adding one to the existing valid chain. So let's explore how we'll create this proof of work system. Many cryptocurrency blockchains, such as Bitcoin, use a proof of work system inspired by a system called Hashcash, which was created in 1997, and it was originally developed in order to prevent the problem of email spamming, as well as denial of service attacks that could overload web servers. So a proof of work system inspired by Hashcash works like this. At any given point, there's going to be a level of difficulty in the system. Depending on this difficulty, when miners try to add a new block, they will have to find a hash value for this block that matches the difficulty. For this matching, miners have to find the same number of leading zeros as the current difficulty for the generated hash of the new block to add to the chain. Now, if you try to find this number of leading zeros randomly and try to get lucky by creating a hash, this becomes exponentially harder as the difficulty rises. So in order to solve the problem of the proof of work, a miner will have to generate a ton of hashes in order to eventually find one that satisfies the difficulty. So they will regenerate new hashes for the same block based on the block data, as well as an adjusting value called the nonce. By continually adjusting this value, the miner can generate new valid hashes for the current block until they find one that satisfies the difficulty. So the nonce value starts at 0 and increments upward until a nonce is used that has a matching number of leading zeros according to the set difficulty. Overall, this act of generating new hashes with changing nonce values takes a decent amount of computational work. Hence, finding a nonce that unlocks a hash that meets the difficulty requirement is that very proof of work. By the way, that term nonce originates from number used once. Shorten that and you get number once. Shorten that, you get n once. You say that quickly and you get nonce. So you use the number once and then change n to something else and keep using it once until you get a valid hash. So regarding the difficulty adjustment, there's one more detail to clarify. In our system, we're currently using the hexadecimal form of SHA-256. For example, the SHA-256 equivalent of foo in hexadecimal form is 2C2, 6B4, and onward. Overall, the hexadecimal form allows us to represent a SHA-256 in 64 characters that range from 0 to 9 and A to F. However, Bitcoin uses the binary form of the hash, meaning the hash will consist of 256 zeros and ones. So the binary form of a SHA-256 hash of the string foo is 00101110 and onward. This means that their difficulty adjustment is based on finding a number of leading 0 bits. Therefore, the difficulty can raise much higher as there are 256 characters in a 256-bit binary string versus a 64-character hexadecimal string. So we're going to explore this more deeply within code in our blockchain project. We'll take a look at both the hexamal and the binary form and compare which is more optimal in terms of adjusting the difficulty. Overall, finding the right combination of the data, nonce, and last hash to meet the leading zeros difficulty requirement takes quite a bit of computational work. This is why the act of finding a block is called mining. The analogy is that it's a grind to find the treasure of a valid hash. Once a miner has successfully mined a block, then they have the rights to submit their block with a found nonce value to other miners. Then other miners, then knowing that nonce value, can quickly verify the valid block and then add it to their chain, without having to redo the same computational work. So, because of this difficulty setting, blockchains can also control an overall mining rate for the system. If it's taking a long time for miners to add a new block, then it will raise the difficulty requirement. Likewise, if it's taking miners a while to add new blocks, then we should lower the difficulty. Overall, the difficulty will raise and lower to bring the average rate at which blocks are added to the system closer and closer to the set mining rate that we have. Bitcoin, for example, has a goal of adding a new block to its chain every 10 minutes. So as more miners are added to the network and more computational power is devoted to the system, the higher the difficulty of solving this proof of work algorithm becomes. The constant adjustment of this difficulty setting keeps the rate of blocks being added to Bitcoin at a steady rate of 10 minutes. This leads us to the interesting scenario of what is called the 51% attack on a blockchain with a proof of work system. The 51% attack is a scenario where a dishonest miner has more than at least 51% of the computing power of the entire blockchain network. Thus, they would have the power to replace the current blockchain with one in their favor, because they could dominate the entire network. They could generate a long enough blockchain that has solved enough proof of work puzzles in order to generate a valid blockchain that everyone else is just going to have to accept, since they collectively only control 49% of the blockchain computing power. However, this proof of work system makes such a situation so computationally expensive that it's ridiculous to spend that cost in order to try and benefit from taking over the blockchain. Take, for example, how much it would cost to take over the Bitcoin network and all of its collective computing power. The current estimates from GoBitcoin.io, as of the end of 2018, are that it would cost more than $9 billion to take over the entire Bitcoin network with a 51% attack. Now, this might not even be the strongest reason why attackers would be dissuaded from taking over the network due to proof of work. So if you have this much computational power already, you might as well benefit from making the blockchain network that much stronger. Otherwise, you'd be undermining the very system that you could profit from. If you have that much computational power, you might as well keep the system strong and support that in order to be the strongest driver of that blockchain system itself. So overall, that wraps up the proof of work system, which was designed to deter dishonest miners in the blockchain network and control the rate at which new blocks are added to the chain. With the proof of work system now well understood, let's build the concept within our application.